All right, let us get going here. We're going to talk more about limits, and then we'll talk about continuity as well, because she's going to talk about continuity tomorrow. It's going to be on your first test, which is next Wednesday, I think, right? That's on. Yeah, okay. So we'll talk about continuity. Tuesday, we'll do some sort of review, and then you guys will have a midterm on Wednesday. All right, cool. Also, FYI, I will not be around tomorrow afternoon for office hours and CADs. Driving to Wairika, everyone's favorite place to go. So yeah, so don't look for me tomorrow. I won't be around. And neither will Sarah. So yeah. Anyway, let's get going. So limits like this, limit is x goes to 0 of 8 over x minus 16 over x squared plus 2x. The first thing we should always do is try to plug it in. But obviously, if you try to plug in 0, you're gonna get division by 0. Now, unlike some of the previous problems we've seen where you get division by 0 and they're like, oh, it's plus or minus infinity. We have kind of a different thing here because one, it's not a one-sided limit, right? It's a from just 0, not from the right or from the left. And we also have 2 divisions by 0. We have 8 over 0 and 16 over 0. So when you have something like this, before we kind of do anything else, we should just try to get this as one fraction. We should get a common denominator. Now I'm going to be kind of smart about this. Say, well, I could multiply this by x squared plus 2x over x squared plus 2x, and this by x over x. But if I'm a little bit more careful, I might recognize that the right-hand thing here is really just 16 over x times x plus 2. And so really, all I have to do is multiply 8 over x by x plus 2 over x plus 2 to get a common denominator. And that's what I should do. So multiply this by x plus 2 over x plus 2. And then I'm going to have, let's see, a limit as x approaches 0 of 8x plus 16 minus 16 all over x times x plus 2. I still don't feel very good about this, but at least it's something. And now I can try plugging in 0. It's still not going to get me. Actually, plugging in 0 gets me somewhere slightly different. Now when I plug in 0, I have a 0 over 0. Right? If we plug in 0 to the top, you get 0 plus 16 minus 16. Plugging 0 to the bottom, you get 0 times 2. So it is a 0 over 0. That's good news in some sense because it means we're probably going to get something relatively reasonable happening. Let's simplify. So obviously we should cancel the 16s. And then you have 8 times x over x times x plus 2. And then we can cancel one of those x's. So this 8x and this x here, excuse me, the x's do cancel. And so then I'm left with the limit of x approaches 0 of just 8 over x plus 2. And now we can actually substitute in 0 for x, and we're going to get 8 divided by 0 plus 2, which is just 8 over 2, which is 4. So often when you have fractions, the way we usually kind of want to put them together is with a common denominator. Like we want just one fraction because maybe that'll make it easier to see what's happening here. There's something else like that too. Oh yeah. Oh yeah. Let's look at one other kind of funky thing. Let's call that number 1. We'll do a couple of these next ones. So let's say I wanted to find the limit as x approaches 0 of the absolute value of x divided by x. It's kind of a very classic example. So you're not sure about a limit. Sometimes you have to look at the right and left-hand side because this absolute value of x function is actually a piecewise function. I remind everybody that the absolute value of x is equal to just x if x is already positive. But if x happens to be negative, then you have to negate the negative to make it positive. And then you put the equals part on whichever part you want. It doesn't matter. I'm going to put it here. So what we're going to do is we're actually going to look at the left-hand side and the right-hand side. The left-hand side meaning the limit as x approaches 0 from the left of the absolute value of x over x. Okay, now let me ask everybody. If x is left of 0, is x positive or negative? Everybody. Right, we're left, we're negative. So, okay, fine. So then, if we're on the left side, that means we are less than 0. So absolute value of x is equal to negative x. So we're going to replace the absolute value of x with negative x. And if we tried plugging in 0, we'd get 0 over 0. But then negative x divided by x, the x's cancel, and you get the limit as x approaches 0 from the left of -1. And I imagine your teacher has probably said this, but just in case they haven't, when you take the limit of a constant, you always just get that constant. So the limit as x approaches, who cares, of a constant is always just going to be that constant. Similarly, if we look at the right-hand side, the limit as x approaches 0 from the right of the absolute value of x over x, we get the limit as x approaches 0 from the right. Well, if x is positive, which it is when x is on the right side of 0, then the absolute value of x is just x. And x divided by x is just 1. So this is the limit as x approaches 0 from the right of 1. And once again, the limit of a constant is just a constant. And now here's the bad news. These don't match. -1 and 1, not the same, which means limit from the left and limit from the right are doing different things, which means the overall limit doesn't get to exist. Question, Tara? Sure. But that's it. So when you're going to negative infinity or to positive infinity, you aren't approaching the same number. They're two totally different things that kind of, in some sense, don't have anything to do with each other. Meaning, it's okay if the limit to negative infinity and limit to positive infinity have totally different values. That doesn't mean one of them does or does not exist. Or actually, yeah. Oh, graphically, here's what this looks like. So this function, well, I will just point, so everybody, for 1 second, think of a positive number. Any positive number you like, just think of it. Okay. Now take that positive number, take the absolute value of it, and then divide by that same positive number. All right. What do you all get? Right. What if you did it with a negative number, though? Take a different negative number, any negative you want, take the absolute value of it, okay, and then divide by that negative number. Now what do you get? Right. Did you all pick the same negative number? No, right? It doesn't matter what negative number you pick, this function, absolute value of x over x, is always equal to -1 if you pick a negative number. So for negative, always going to be equal to -1. And if you're positive, when x is on the right, it's always going to equal +1. So this is what this function looks like. And notably, I think we can see here, this function is 1, undefined at 0, but 2, the limit as x approaches 0, right? We're not matching up. The right side and left side do totally different things. Cool. Let's look at one just a little. So this is, so what I would say is generally, this is how you approach limits of, oh, actually, that's interesting. I don't love that, actually. Interesting. Not a fan. Anyway, let's take a, I just want to look at this problem that's similar to your homework question, just because I'm looking at it. And this one is not as fun as I want it to be, but oh well. Let's say we want to do the limit as x approaches -5 of 5 minus the absolute value of x over 5 plus x. 5, yep, sure. My gut, I don't know. I'm actually not sure what's going to happen. Sometimes you just try stuff. Here's what I want to point out, though, and here's where I was probably going to do the wrong thing. I was thinking, oh, well, on one side of -5, the absolute value, but the absolute value of x is the same as it ever was. It's just x if x is positive, and it's -x if x is negative. All right, if x is approaching -5, is x positive or negative? Not a trick question. It's definitely negative if we're approaching -5. So what we're going to do here is you're just going to start off right off the bat by rewriting this as the limit as x approaches -5 of 5 minus, well, since x is negative, I need -x. Oh, that looks like it's going to cancel out. 5 plus x over 5 plus x is just 1. That's just the limit as x approaches -5 of 1, which is still 1. Cool. I didn't actually expect that to happen. Let's do one more, which is a little more interesting in my opinion. Maybe, sure. How about the limit x approaches 6 of absolute value of, sure, why not? X squared minus 5x minus 6 over x minus 6. Ooh, that's interesting. Yeah. I don't know if I like this so much. So let's simplify this. Let's factor the top. I think the top factors as x minus 6 times x plus 1. Yeah, that seems right. Here's what I really want you to see. You can't cancel those x minus 6s yet. In an absolute value is different than not being an absolute value, and they do not cancel each other out automatically. So what we have to do here is we actually do have to look at both sides of 6. So let's look at the limit as x approaches 6 from the right-hand side, the bigger than 6 side. So if I do that, then the absolute value of x minus 6 times x plus 1 over x minus 6. Well, if x is bigger than 6, then x minus 6 is positive. So I can bring that x minus 6 outside of the absolute value. Or what I should really actually, I should be better. Technically, what we're going to do is we're going to say the absolute value of a product is the product of the absolute values. That's always true. If you have the absolute value of two things multiplied together, you can take the absolute value of each one and then multiply it together. Either way you do it, it's going to turn out to be positive. And then since we're a little bit bigger than 6, x minus 6 is positive. And so the absolute value of x minus 6 is going to be just x minus 6. And then you can totally cancel those out and plug in the 6 and get the absolute value of 6 plus 1, which is 7. Okay, let's look at the other side. If we approach 6 from the left. So now I'm going to skip from this step to this step here. This is where I think it's actually interesting. So x is a tiny bit less than 6, which means that x minus 6 is negative. How do we turn a negative thing into a positive thing? Right, exactly. So I'm going to take that x minus 6, the whole entire x minus 6, and multiply it by -1. So it's going to be the limit as x approaches 6 from the left of -1 times x minus 6 times the absolute value of x plus 1 over x minus 6. The x minus 6 is still cancel, but now when we plug in 6 for the remaining x's, we get -1 times the absolute value of 6 plus 1, which is -7. So the limit from the left and the limit from the right don't match up. The right-hand limit's +7, the left-hand limit's -7. The overall limit does not exist. Which always feels, I mean, I know it doesn't really matter, like who cares what the answer actually is? Still feels disappointing. I want those limits to exist every time. Well, they don't always exist. Okay. Let's talk about another special 0 over 0. So most of the time, like we were saying in class on Tuesday, if you see a 0 over 0 type of limit, usually means you have to use some sort of algebra. Often factoring and canceling, sometimes multiplied by a conjugate. There's also one we didn't get to where you have like using a common denominator, which maybe I should, even though there's none of these on your homework, I feel like I should still throw in your way. Just one more example before we get to the special one. So one more 0 over 0 type. The 0 over 0 types of limits. If you see a 0 over 0 type of limit, what you want to do, you want to do algebra. Just as a reminder, just so you all remember what I said before. And the algebra we do, well, you can either factor and cancel. I will say almost always at some stage for these 0 over 0 ones, you're usually going to end up doing some factoring and canceling. maybe not at the beginning, but definitely probably by the end. Step 2 or thing 2 you might try is if you see a square root, we know we're going to multiply by the conjugate. And thirdly, one we didn't talk about before is that if you see fractions in fractions, we're going to get a common denominator. Let me show you what I mean. So let's say we have the limit as x approaches 5. I'm making stuff up on the fly, always goes so well. Let's say we have x minus 5 on the bottom and sure, x over 10 minus 1/2 on top. You plug in 5 for x. I should never pick 5. My 5's never really good. You plug in 5 for x, you get 1/2 minus 1/2 over 5 minus 5, which is 0 over 0. So this is definitely a 0 over 0 type. Meaning we need to do something. And here the something is to get a common denominator where you have the fractions of the fractions meaning on top. I'm going to need a common denominator. So I'm going to rewrite this as the limit as x approaches 5 of, so let's see, my common denominator is just going to be 10. So I'm going to say I've got x over 10 minus 1/2 times 5 over 5, all over x minus 5. And then I'm going to simplify. Limit as x approaches 5 of, let's see, I'm going to get x minus 5 all over 10. And here's a good trick. Instead of dividing all this by x minus 5, let's multiply all this by the reciprocal of x minus 5. I feel like it's just easier to not have fractions in fractions that way. It really is, I will point out, this is actually the same as x minus 5 over 10 all over x minus 5. It's just nicer, I think, to write it this way, because then it's easier for me to see that the x minus 5s get to cancel each other out. So we're left with limit as x approaches 5 of 1/10, which is just 1/10. Okay, I fully admit that one was kind of boring. I mean, I know, okay, it's fine. Doesn't have to, and not every math problem has to be exciting. Let's do one more like this just to kind of drive it, because I realized that I didn't make a mistake, just I know how to make it more interesting. So have the limit as x approaches 6, sure, of 4 over x minus 2/3 all over 2x minus 12. Exciting times. Another 0 over 0 type. So here, we're also going to get a common denominator where we have the fractions subtracted or added together. So in this case, I need to multiply 4 over x by 3 over 3 and 2 over 3 by x over x. And in the denominator, I'm going to factor out the 2 because I can. Because I can see that if x is approaching 6 and that's making me have a 0 over 0, I'm probably going to need to factor out and cancel out an x minus 6. That's what's making me have the problem. All right, so in the numerator here, I have the limit as x approaches 6. Let's see, I have a 3x as my denominator, and 4 times 3 is 12, and 2 times x is 2x. All over 2 times x minus 6. Have you all ever seen when someone like takes a fraction like this and just rewrites it as like 12 minus 2x over 3x times 2 times x minus 6? It's totally valid, but it always feels like someone's kind of like just saying, really, that just moves up there? It really does. I just want to point out that you can do this in a few steps if you really want to. I can write this as 12 minus 2x over 3x times the reciprocal of 2 times x minus 6 over 1, which is 1 over 2 times x minus 6. And then we can just write this as one fraction. Limit as x approaches 6 of, on the bottom, I'm just going to have 3x times 2 times x minus 6. And what would be smart to factor out from the top? 2, sure, I'm going to go with 2. I like 2. So the 2's cancel, it's good. Okay, now here's something that comes up actually semi-regularly. What is 6 minus x divided by x minus 6? Interesting. it's actually always, unless x is 6, which is not because we're approaching but never equal to 6. And that's what the limit says. If x isn't 6, this is always going to equal -1. If you subtract things, right? So pick a number, pick any number that's not 6. 6 minus that number, and then that number minus 6 are just opposites of each other. So I'm picking 10. 6 minus 10 is -4. 10 minus 6 is +4. -4 divided by 4 is -1. And it works no matter what number you pick. The other way you could have seen this is we could have factored out a -2 instead. If we factored out a -2, we would have had -2 times -6 plus x over 3x times 2 times x minus 6. And then -6 plus x and x minus 6 are actually the same as each other. So those cancel. And you end up with plugging in 6, -2 over 3 times 6 times 2. The 2's cancel and you get -1 over 18. Or here you can say, well, these are going to cancel. And when they cancel this way, they leave behind a -1. Then you have the limit as x approaches 6 of -1 over 3x. And when you plug it in, you get -1 over 18. Same answer either way. Okay. I feel like I've done my due diligence now. I've shown you the thing that I felt like I had to show you. I don't think there are any homework problems that actually make you do this stuff, but it doesn't mean you shouldn't see it. Right? Just because it's not in the homework doesn't mean it's not valid. Daniel.
Instead of taking out the 2,
Yeah.
you could have just taken out, you can take out -2.
Right. Yeah. Right. That's exactly what I wrote down here. Yeah. Yep. Yeah. Okay, so also from here, if you don't like canceling this, you can factor out a -1, and then you'd be left with a -6 plus x, which is the same as x minus 6, and then they cancel this nicely. So these are most of the 0 over 0 types of limits. Although I guess we did see one earlier today, right? This was also a 0 over 0 where we didn't really do algebra. We used the fact that this was a piecewise function to kind of look at it from both sides. But now there's another type of 0 over 0 limit. This one, the limit as x approaches 0 of sine of x over x is a very special 0 over 0 limit. Pardon me. So I think you've seen this in class already. There is a geometric proof of this that I don't think is really worth. Well, actually, a geometric proof of what? I didn't say what the limit was yet. The limit is what? There is a geometric proof where you can kind of do a squeeze theorem thing, which we're going to talk about in a few minutes here, to show that this really does get squeezed between two things that are getting closer and closer to 1. But it's kind of a lot. Here's what I would recommend instead. Here's the graph of sine of x over x. And we can see that if you follow along, as x gets closer and closer and closer and closer to 0, the sine x over x values are getting closer and closer and closer to 1. Super close, very close, right? We're getting closer and closer and closer. So really, really close to 1. And then when you get to 0, it's undefined. Oops, 0, right? Undefined. Now that 1 to the right there, that's not really a 1. That's just, it got so close to 1 that they just said 1. There's like 0.9999999. They're like 1. The point is here, just like with any limit, the point is that as x gets closer and closer and closer to the thing that x is approaching, the y values happen to get closer to a particular value. In this case, those y values are getting closer and closer to 1. So nice. Now here's what I really would like you to see. It doesn't matter what's in there, as long as what's in there is going to 0 and the bottom is the same thing. So you can have something crazy like, I don't know, x to the 5th plus 7x minus 2. Oh, no, minus 2 is going to be bad. Not minus 2, because the stuff has, well, in fact, we'll look at that in a second. Over the same thing. And look, we're still getting, can you see the 1? Yeah, we're still getting closer and closer to 1 as you get closer and closer to 0. So here's the thing I really want you all to recognize. As long as you have sine of some stuff over the same stuff, and that stuff is going to 0, then your limit will be 1 every time. But the stuff has to be the same, and it has to be going to 0. So for instance, if I did throw in a +2 inside the sine function, And down here, no longer getting 1. Right, as x approaches 0, I'm getting something that's definitely not 1, right? Because it's totally defined there. So it has to be both things going to 0. The other thing I'll point out is that the inset, you don't have to necessarily have x going to 0 itself. For example, you had 1 over x there. Whoops. And 1 over x here. Well, as x is going to 0, you got problems. But as x is going to infinity, as we go way, way out to the right here, the y values are getting closer and closer and closer to what? Everybody. Thank you, yes. And that's because the stuff inside the sine function and the stuff we're dividing by is the same. And as x gets really, really big, the stuff in the sine function and we're dividing by is getting closer and closer. So that's what I really want you all to take to heart, is that for this limit to be what it's going to be, we generally like to write something like the limit as x approaches whatever of sine of some stuff over the same stuff, has to be the same, is going to equal 1 as long as the stuff that you're taking sine of and dividing by is approaching 0. Much of the time, it'll be just x is going to 0 and whatever, and there will also be going to 0 because it's just a multiple of x. But that's the gist. You want sine of something over the same something. So, for example, we could ask the limit as x approaches 0 of sine of 9x over 9x. The stuff is the same, and the stuff is definitely going to 0. So that limit is going to be 1. And I don't think we need to show any work. We're going to show more work in a minute here, but let me just give you one more example of something kind of weird. I can do the limit as x approaches 2 of sine of 3x squared minus 12 over the same exact thing. I've met the criteria. It's sine of a thing over the same thing. And very specifically, is the thing going to 0? If I plug in 2, 3 times 2 squared is 12. Yep, it's going to 0. So since this is a sine of 0 over 0, and the zeros are the same, this limit has to be 1. No question about it. Which is great. But then what we do is we start asking more interesting things like, what if I want to find the limit as x approaches 0 of sine of 9x over 5x? The stuff is no longer the same. It's easy to fix, and there's a couple different ways people like to do it. I'm going to show you the way that I think works the best. So I like to do what I call the wish method. And I'm going to ask myself, what do I wish I had beneath sine of 9x? Well, I wish I had 9x. So I'm going to make my wishes come true. I'm going to write the limit as x goes to 0 of sine of 9x over 9x. But that's not the same, right? Because I still really had a 5x in the denominator. And I can't just multiply by 9x in the bottom without also multiplying by 9x in the top. That's the way I like to do it. I like to say, well, I want this, and then I need all this for it to still be equal and to be looking right. But then x over x cancels. Now, long way, short way here. If I was doing this the short way, I would just be like, boom, this is equal to 1 times 9/5. Because the limit of as x goes to 0 with sine 9x over 9x is going to be 1 times, and then 9 over 5 is just 9 over 5. Which is 9/5. If I knew my teacher wanted me to show more work, I might do the following. I might write this as the limit as x goes to 0 of sine of 9x over 9x times 9/5. And then I would use one of my limit rules to say that the limit of a function times a constant, that constant is allowed to move out in front of the limit. And that's going to equal 9/5 times the limit as x goes to 0 of sine of 9x over 9x. And then I'm like, that's 1. So I get 9/5 times 1, which is 9/5. I don't think you ever need to show all this work unless you're like taking a test and you think your teacher wants to see all this work. But really, we're like, we know that this is going to 1, so we're going to get 1 times this constant. Something important. This function, sine of 9x over 9x, is not equal to 1. It's only getting close to 1 when x is getting close to 0. But that's a whole function that has many, literally infinitely many numbers of values, right? So I don't want you to get in your head that like sine x over x equals 1. It doesn't. It's the limit as x approaches 0 of sine x over x that is equal to 1. We're just saying as x gets close to 0, the y values get close to 1. That's all we're saying. But we kind of get in this habit, like, oh yeah, I like to say it's not equal to 1, it goes to 1 as x goes to 0. Let's look at a few more examples. Also, please do stop me or interject if you have questions. And we're about to get to the infinity ones too. So like, because I know there's some infinity ones on the homework. We're about to see those. Let's look at a couple more of these. So let's say we want to do the limit as x goes to 0 of, sure, let's make it a little more interesting. Sine squared of 5, no, why 5? Why do I pick the number 5? Double right, over 3x squared. So when I write this out, I really like to write it out the following way. Sine squared of 5x just means sine of 5x times sine of 5x. So I'm going to write this as the limit as x goes to 0 of sine of 5x over a denominator that's going to be determined, and then another sine of 5x over blank, and then I also have another fraction with something over 3x squared. So currently, as I've written this, although it looks kind of weird, nothing has changed. It's still the same thing. Sine of 5x times sine of 5x all divided by 3x squared. But now I'm going to ask myself the question, what do I wish was beneath sine of 5x? And the answer is, but if I divide by something, I also have to multiply by it so I don't change the whole value. And then I'm going to ask the same question here. What do I wish was beneath that sine of 5x? Oh, another 5x. I'm going to multiply by another 5x. Here the x's are going to cancel. Great. This x times this x is x squared, and it definitely cancels with that x squared there. So then here's what I would say my answer is. I would say my answer is, well, sine of 5x over 5x goes to 1. Sine of 5x over 5x goes to 1. And 5 times 5 over 3 is 5 times 5 over 3. The x is canceled. 25 over 3. Let's do 2 more of this variety and then we'll switch it up a little bit. Sure. Let's look at something that looks kind of similar, but is actually quite a bit different. I say things and then I actually have to do them. Sure. I want the limit as x goes to 0 of sine squared of 6x over just 6x. Good question. So same idea. Limit as x goes to 0. I'm going to have now technically, well, no, I'm going to write sine of 6x times sine of 6x. I really, if I wanted to, I could use the exact 6x I have right here and just put it underneath. But I don't know. I feel like it's good to just kind of use the same pattern. So I'm going to do this, even though I'm making it slightly more. Okay, so what do I want there? A 6x. What do I need there? A 6x. What do I want there? A 6x. What do I need there? A 6x. Okay, and one of these 6x's does actually fully cancel out. Great. And now if I let x go to 0, here's what happens. I get, well, sine of 6 over 6x goes to 1. And sine of 6x over 6x goes to 1. And where does 6x go to? 0. So the whole thing is 1 times 1 times 6 times 0, which is 0. So sometimes you get 0 if you don't have like the same number of x's as sine, essentially. Here I have a sine squared, here I have an x to the first, so I have kind of an imbalance there. Yeah, that seems all right. Let's look at the other kind of variety of this. Let's say I want to find the limit as x goes to 0 of, sure, 1 minus cosine of 4x all over 2x. Let's make it more interesting. Let's make it 2x squared. That'll be more exciting, I think. Probably, who knows? So When you see a 1 minus cosine or a 1 plus cosine, or later on in life, a 1 minus sign or a 1 plus sign, there's a trick. And the trick is for those things specifically to multiply by the conjugate. You'll see why in a second. So we're going to multiply this by the conjugate of 1 minus cosine of 4x, which is 1 plus cosine of 4x. And of course, if you do it on top, you have to do the same thing on the bottom. And just like with the square root conjugates that we were doing last class, you want to not multiply with the things that aren't actually conjugates of each other. So we're just going to leave the denominator as 2x squared times 1 plus cosine 4x, and we're not going to like simplify it or FOIL it or anything. So write this as the limit as x goes to 0 of 2x squared times 1 plus cosine of 4x. And then on top, we are going to multiply it out. When we multiply it out, just like anytime you multiply out conjugates, the middle terms cancel. You get 1 times 1, so 1 squared, minus cosine plus cosine, those cancel each other out. And then finally, a minus cosine times a positive cosine is going to be a negative or minus cosine squared of 4x. Okay, but there's a point to this. And the point is that there's a trig identity for 1 minus cosine squared of 4x. I'll remind everyone just because it's, in fact, there's a couple identities I'm going to write down on the next page. So on the next page here, just for a second, I just want to remind everybody of 2 important identities. One, what I like to call the most famous trig identity, sine squared of theta plus cosine squared of theta is equal to 1. The alternate slightly version of this that we're going to be using right now is that sine squared theta is equal to 1 minus cosine squared theta. And then the other one I want to point out, just because I saw it, it kind of comes up in one of your homework problems, is if you divide everything here by cosine squared, sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equal to 1 over cosine squared theta. Sine divided by cosine is everyone's what favorite trig function? Maybe not your favorite, I don't know. What you do if you get too much sine? You get tangent, but it's tangent squared. And then cosine squared divided by cosine squared is 1. And then 1 divided by cosine is secant. So 1 divided by cosine squared is secant squared. Okay, I don't usually write it this way. I usually write it as 1 plus tangent squared theta equal to secant squared theta. And the reason I write it this way is because one time a student said to me some unforgettable words, I tan and get sexy. You will never forget this trig identity if you remember that I tan and get sexy. So I tan and get sexy, unforgettable. 1 plus tangent squared theta equals secant squared theta. And you definitely want to use that trig identity when it comes to, oh God, what problem was it? I don't know. It was a problem where I saw 1 plus tangent squared somewhere. I don't know. It's somewhere in your homework. It's, yeah. Oh, it's problem 9 in section 2.4. You definitely want to use that trig identity there, I think. Back to this though. There are other trig identities, but those are 2 that I think are pretty important. We're going to replace 1 minus cosine squared of 4x with sine squared of 4x. The angle does have to be the same. So whatever angle is in here, it has to be the same as in there. And then you've still got a 2x squared times 1 plus cosine of 4x. Okay, now I'm going to do the usual kind of thing I do. I'm going to break this up into sine of 4x over blank times sine of 4x over blank times blank over the whole entire denominator. 2x squared times 1 plus cosine of 4x. And then, of course, beneath each sine of 4x, I wish I had a 4x. Then these 2 x's here cancel out with the x squared down there. So I'm left with sine of 4x over 4x, which goes to 1. Sine of 4x over 4x, which goes to 1. Notice I'm not writing the limit anymore because I'm taking the limit. And then finally over here, I get 4 times 4 over 2 times 1 plus cosine of 0. What's cosine of 0? 1. So I really have 1 times 1 times 16 over 2 times 2, which is just 4. Neat. I think the problems you have like this don't have an x squared on the bottom, they just have an x, so I think you end up getting 0 as your answer instead of something more exciting like 4, whatever. Oh, and then we need to talk about the other ones, which are okay, cool. So what if on the other hand I said, not that. I wanted to find the limit as x approaches infinity of sine x over x. So be careful. It's really easy to accidentally think this is going to be 1. But it's not 1 because although we have sine of a thing over the same thing, the thing is not going to 0. So it's not 1. I just want to make that extra clear. Here's what I always think about when I think about a limit to infinity with sine or cosine. It's a clue. When you have sine of something that is getting infinitely large, that sine function is just doing this, right? I mean, just in case, just so you all can see it again. What? Why aren't you doing the thing? Sorry, apologies. Just want you everyone to see it. Oh, I have to click on it. Sorry, there you go. Okay, cool. Here's your sine function. Oh my gosh, maybe not. Here's your sine function. And it just goes on and on and on and on, right? I mean, I think, right, it never stops. Yeah, it never stops. Okay. So sine just keeps doing this up and down, up and down, up and down, periodic oscillating kind of thing. And it never gets close to any particular value. So here's what I always like to say about sine. If I know that I'm just going off and off and off and I don't have any kind of value to be close to, I can always say that I know that sine of x is always between -1 and 1. It's also true for cosine, right? In fact, in a similar way, let's do the limit as x approaches infinity of cosine of x over x as well. We'll do that one in a minute. So then the usual kind of plan of attack for something like this is after you have observed that sine is between two numbers, -1 and 1, do you then want to manipulate this inequality to make the middle part look like the thing you want to take the limit of? And it's really just do the thing that gets you there, meaning I have sine x over x. I only have sine x here, though. How do I get it divided by x? I divide everything by x. You literally just do the thing you want to happen to make it happen. So divide by x, divide all things by x, and you get -1 over x is less than or equal to sine of x over x is less than or equal to 1 over x. And then we ask ourselves, well, what's happening to these outer things? The limit, in fact, we can actually just take the limit of each part if you really want to in the inequality. The limit as x goes to infinity of -1 over x is less than or equal to the limit as x goes to infinity of sine of x over x is less than or equal to the limit as x goes to infinity of 1 over x. Okay, I know we've done this a few times. As x goes to infinity, what happens to 1 over x? Right. And as x goes to infinity, what happens to -1 over x? Also goes to 0. So the limit as x goes to infinity of sine of x over x is less than or equal to 0 and is bigger than or equal to 0. You have no choices. It must be 0. So by the squeeze theorem, or sandwich theorem, as some people call it, the limit as x goes to infinity of sine of x over x is 0. And it would be true whether we went to infinity or to negative infinity. Right? I think you all can see that if I did the limit as x went to negative infinity here, I'd still be getting 0, and negative infinity here, I'd still be getting 0. So this is usually what I think about when I see a limit where I have a sine or cosine, specifically sine or cosine, and the inside of the sine or cosine is getting infinitely large or negatively infinite. I would do the exact same thing here. I would say, okay, great. Cosine x is between 1 and -1. Divide everything by x. And then I usually do it this way. I don't actually like to write the whole limit inequality. I usually just say, well, the limit as x goes to infinity of -1 over x, bless you, is 0. And the limit as x goes to infinity of +1 over x is 0. So by the squeeze theorem, the limit as x goes to infinity of the middle part has to be the same thing. Now, this only works if both the right-hand side and the left-hand side have the same limit value. They cannot be different at all. If they're different at all, you don't get to say, oh, well, it's the same. So they have to be the same. There's a couple more examples I want to do. Sure. Okay, let's do that one. That one's exciting. So, yeah, question, Lily. No, that they both end up equaling 0, right? So this and this are the same. So that means that the thing in the middle has to be less than or equal to the thing and bigger than or equal to the same thing, and less than or equal to the number and bigger than or equal to the same number. You are that number. Yeah, that's what I mean by the same, is that the value. And often it'll be 0. It doesn't have to be 0, though. It can literally be anything. Yeah. So let's see here. Let me look at one quick thing here. Yeah, sure, that's fine. Okay. Sure, that's that's a, yeah, that's good. Okay. I don't love that. Let's make it slightly more interesting. Sure. Let's say I want to find the limit as x approaches infinity of 5x squared plus cosine of 7x over 3x squared plus x. And to me, this has the hallmarks of a problem that must use the squeeze theorem, because I have a limit where there's a cosine or a sine, and the insides of the cosine or sine are going to infinity. Those to me are the things that say I probably need to use the squeeze theorem. There's a couple ways to do this. I'm going to show you the way that I like better, but I'll point out that there's another way. So here's what I would do. I would start with this. Start with your trig function, cosine or sine, between 1 and -1. And now we're going to make this look like that, specifically the middle part. So I'm going to add 5x squared to every side of this inequality. 5x squared minus 1 less than or equal to 5x squared plus cosine of 7x less than or equal to 5x squared plus 1. And then we're going to divide everything by the denominator. So 5x squared minus 1 over 3x squared plus x less than or equal to 5x squared plus cosine of 7x all over 3x squared plus x. And my 5s and my 3s are starting to look too similar. Finally, 5x squared plus 1 over 3x squared plus x. And now I'm going to ask you all, if I take the limit as x goes to infinity of 5x squared minus 1 over 3x squared plus x, without doing any work whatsoever, we all probably know that this limit is what fraction? 5/3, right? Because we see that the degree on top and the degree on the bottom are the same. So the limit is just the quotient of those leading coefficients. And similarly, that's also the limit as x goes to infinity of 5x squared plus 1 over 3x squared plus x. And since the limit of this is 5/3 and the limit of that is 5/3, the limit of the thing in the middle has to be 5/3. Where did it go? Well, so it didn't go anywhere. Right. The thing is, when you're taking a limit like this using a squeeze theorem, you're never actually taking the limit of the middle part. You're taking the limit of the outsides of the compound inequality and then saying, oh, well, if the limits of those are the same and what value, then the limit of the middle thing has to be the same. It's squeezed to it. So this has to equal 5/3. One more, and then we'll move on. One more of my favorite ones. Let's do the limit. X approaches 0 of x squared times sine of pi over x. Now I'll point out this does meet the criteria I was talking about. I have a sine or cosine And the inside of the sine function is getting infinitely large. I divided by x gets really, really, really large as x gets closer and closer to 0. So it totally is a valid thing to do here, to use the squeeze theorem. So we're going to say that sine of whatever we've got is between 1 and -1. Always true. Why these problems work out for that. And then we're going to multiply everything by x squared. I'm going to have negative x squared less than or equal to x squared times sine of pi over x less than or equal to 1. Sorry, less than or equal to what? That one's not right. What should that be? Right. Sorry about that. And then we're going to take the limits of the outer parts. So the limit as x goes to 0 of negative x squared is, just plug it in, you get 0. The limit as x goes to 0 of positive x squared is also 0. So one more time, by the squeeze theorem, we have to say the limit as x goes to 0 of x squared times sine of pi over x must be 0. The reason I like this one is because the graph of it's kind of nice. I'm sorry. Change that thing. Cool. Let me show you what I mean. I'm going to cover this up for just a second. I promise I'll bring it back. Here's the graph of x squared. Oh, maybe it's there. I promise you. There's the graph. And there's the graph of minus x squared. So you can see that as we come, like if you're between these two functions and you're getting closer and closer to 0, well, your y values are going to get smushed between some things that are getting closer and closer to 0. And they are. If we show this one, hey, look, there's your x squared times sine of pi over x, and it's funky, but even though it's bouncing back and forth, as you get closer and closer to 0, it's just getting smushed in between two numbers that are getting closer and closer to 0. So that's why the limit is 0, even though it's got this infinite oscillation back and forth. Kind of neat. It's really neat. I mean, zooming in on this, it's kind of cool. I'm like, oh, cool. Yeah. All right. Anyway, not a good use of your time. So let's move on. Yeah, we got 25 minutes left. We can talk about some continuity. So, in my opinion, the easiest way to talk about continuity is to talk about things that are not continuous. Continuity. Here are some functions, just some pictures of functions that are not continuous. Sure. Well, sure, I'll draw right there. Let's say this point, I don't really care what this point is. Let's say this is the point 6, 12. This function is not continuous. Not continuous. Specifically, the reason it's not continuous is f of 6 is undefined. I will point out that this function that I just drew is continuous almost everywhere. It's continuous literally everywhere other than 6. But even being discontinuous at one point is usually enough to say or to describe the function as being discontinuous. So yeah, function not continuous, specifically not continuous at x equal to 6. Let me draw another one. Here's another function that is not continuous. I suppose I could say discontinuous. Specifically, f of 3 is undefined. So to be continuous at a particular point, the function has to be defined at that point, but that's not enough. That's one requirement. Let's look at a couple more pictures that I'm going to draw here. Let's say we have something that looks like this. This is the point, I don't know, 3, 4, and this open hole here is the point 3, 7. Function certainly is discontinuous. So I should back up. I like to imagine, well, I don't have to go. I think most people have a fairly okay idea of what it means to be continuous just by looking at the graph. I can look at all these graphs and say they're discontinuous because I can see that to draw them, I had to lift my pen off the paper. That is the very kind of layperson way of describing what continuous is. If I can draw it without lifting my pen off the paper, it's continuous. If I have to lift my pen off the paper, it's discontinuous. And even though, right, you could be like, James, you can kind of draw that. No, but still, no. It's there's like I have to jump over a little tiny hole there. I ever had one like teacher describe it like, imagine there's like a little mouse running on the line, and even that little hole is too far for the mouse to like jump over. So the mouse has to be able to like stay and right here at the mouse. Yeah, that's not going to work out. So this one is discontinuous. F of 3 exists, I'll point out. F of 3 is equal to 4. The problem here is the limit doesn't exist. The limit as x approaches 3 from the left-hand side is equal to 4, while the limit as x approaches 3 from the right-hand side is positive 7. And that means the limit doesn't exist. And finally, one more example of discontinuity. I'm going to draw a thing first. Sure. So here's my function. Notably discontinuous. I had to lift my pencil off the paper to be able to draw it. And let's say that this hole is the point 3, 4, and now this point here is the point 3, 8. So for this function, it's certainly defined at 3. F of 3 is 8. The limit exists. The limit as x approaches 3 from either side is going to be positive 4. But it's discontinuous. These aren't the same as each other. And I really want to make this stick in your head as best I can, because I've seen a lot of people over the years say, once they say that the limit exists, and the left-hand side and the right-hand side match up, they're like, great, it's continuous. Not true. It's only continuous if the limit exists and also the limit is equal to the function value. So that's actually kind of how we typically think about the definition of continuity. So f of x is continuous at x equal to some number a if and only if. I should point out that people abbreviate if and only if as an if with 2 f's. So if you see this, it's written also as if, just in case you ever see that. It's, I don't know, it's lazy, right? It's why we write natural ln instead of log base, because we're lazy. We don't want to write too many letters. So following 3 things. Thing 1, f of a is defined. Thing 2, the limit as x approaches a of f of x exists. And thing 3, which really encompasses thing 1 and thing 2, but it's still nice to break it apart into 3 pieces, is that the limit as x approaches a of f of x must equal the function value. So I will point out, because it is often done this way, the third thing is all you actually need to say. People will often say that the f of x is continuous if the limit is equal to the function value, because them equaling each other implies they both had to have existed in the first place. But it's usually nicer just to break it down into 3 parts. So that's the definition. Let's look at some examples. So I could see, if I was a teacher, if I was a teacher, when I was the person giving the exams in like a calculus class at the other universities I worked at a few years ago, I would almost always ask a question like this. Is the following function continuous at the following points. Specifically, I want to look at x equal to 0 and at x equal to 1. I suppose I should write the function. So here's my piecewise function. Piecewise functions are our primary source of examples of discontinuous functions. So I've got x plus 1 when x is less than 0, e to the x when x is between 0 and 1, and 2 minus x when x is greater than 1. So I'm just going to look at each value of x. So usually when we're trying to determine continuity of a piecewise function, we're really only concerned with the places where we change from one piece to the next. I will say a few things before we do this. Lots of functions on their own are continuous everywhere. Any polynomial is continuous everywhere. Any exponential function like e to the x or 2 to the x is continuous everywhere. Sine and cosine are continuous everywhere. I'll write it down on the next page. But the more broad statement that is usually true is that most normal functions, simple functions, are continuous on their domains, meaning wherever they're defined, they're continuous, which can be a little bit weird, but we'll talk about it in a second. Let's look at this example and then I'll write down those things in a minute. So here, I'm going to look at x equal to 0 first. For x equal to 0, I'm going to check three things. Thing one, is f of 0 defined? Yeah, if I'm going to plug 0 into the middle piece here because that's where x is equal to 0. So f of 0 is just e to the 0, which is 1. A thing two, does the limit exist? Well, almost every time for these piecewise functions, if the limit's going to exist or to find the limit, we're going to have to look at the right and the left-hand side. It's usually going to be defined to be different pieces on either side of whatever x is approaching. So I'm going to look at the limit as x approaches 0 from the left of f of x. If I'm approaching 0 from the left, I'm going to be using the x plus 1 part because that's when x is less than 0. And that's going to equal 0 plus 1, which is 1. And limit as x approaches 0 from the right of f of x. Be careful, I'm not using the 2 minus x part. I'm using the e to the x part. That's where x is immediately to the right of 0. But I know that when I plug in 0 here, I'm going to get e to the 0, which is 1. So yeah, the limit exists. I can say that the limit as x approaches 0 from either side of f of x is equal to 1. And then I can see that the function value and the limit value are both the same value. So I can say, yeah, f of x is continuous at x equal to 0 because the limit as x approaches 0 of f of x is equal to f of 0. Cool. I didn't leave myself enough room for that. I probably can make it fit. So then we're also going to look at x equal to 1. Same deal. Check all three. Well, check things until you don't have to anymore. Meaning, as soon as I should have said, as soon as something fails, as we saw with the first 4 graphs we drew, it's going to not be continuous. If it doesn't exist somewhere, or if the limit doesn't exist, or if the limit and the function aren't equal to each other, any one of those is a good enough reason to say the function is not continuous. So, first of all, f of 1 is going to be e to the 1, which is just e. Just leave like e. 2, limit from the left and the right. So the limit as x approaches 1 from the left. When I'm left of 1, I'm using the e to the x part. The limit as x approaches 1 from the left of e to the x, which is just e to the 1. And then from the other side, the limit as x approaches 1 from the right of f of x is equal to the limit as x approaches 1 from the right of 2 minus x, because that's the piece where x is bigger than 1, and 2 minus 1 is 1. Those are not the same. So the limit doesn't exist. The limit as x approaches 1 does not exist. And that means we are not continuous at that point at x equal to 1. often when this kind of question gets asked, the question is phrased as, where is this function continuous? So I would just end this by saying, I'm putting it over here. This function, f of x, is continuous everywhere except for x equal to 1. So continuous on the interval from -infinity to 1, union 1 to infinity. I find it kind of annoying personally, but that is often how this question gets asked. So we should be prepared to answer it that way. So let me give you a brief list. I guess the list, yeah, the list. A brief list of functions that are continuous in various places. So functions that are continuous everywhere. They're continuous on the entire real number line interval. Any polynomial. Polynomials are kind of like our favorite functions. They are continuous everywhere, and as we will see shortly, they are differentiable everywhere. They have all kinds of great qualities. So any polynomial like f of x equal to 4x cubed plus 5x minus 1, or g of x equal to 2. That's a polynomial, it's just a boring one. Or h of x equal to x to the 99th power minus 9. Just some examples off the top of my head. Anything that where you only have just non-negative integer powers of x added together. Any exponential function. Like e to the x or 2 to the x or 1/3 to the x. Those are all continuous everywhere. Nice. Sine of x and cosine of x. There was one other one I had. Nope, I think that's it. So these are the functions off the top of my head that are continuous everywhere. Now, what we say is that most functions are continuous wherever they are defined or on their domains. Some examples of this. Rational functions, which I always find mildly annoying, but it's okay. For example, f of x equal to 1 over x minus 2, or g of x equal to x cubed plus 5x plus 1 over x squared minus 5x minus 6. These functions are continuous everywhere that they are defined. But I'll point out that means specifically, excuse me, this function f of x is not continuous at 2. It's not defined at 2. So not continuous at next. Similarly here, this function is not continuous at the values of x that make the denominator 0, which are x equal to 6 and x equal to -1. That factors x minus 6 times x plus 1. The rational functions are continuous everywhere that they're defined, or where they're not defined, you typically have vertical asymptotes. And then the rest of the trig functions: tangent, cotangent, secant, cosecant. They are very similar to rational functions in that they have places where you might be dividing by 0. Right? Tangent of x is undefined at every odd multiple of pi over 2. The tangent of pi over 2 is like doing 1 divided by 0. Also, think about the graph of tangent, right? It's got like a million vertical asymptotes. Actually, that's not enough. It's got like an infinity number of vertical asymptotes. And then, oh, one more. Yeah, sure. F of x equal to the natural log of x. Totally continuous. So it's funny because, I mean, we totally say it's continuous on its domain. It looks like this. definitely continuous wherever it's defined, right? There's no discontinuity there. It's just that it's not defined when x is 0 or negative. So yeah. And then even roots. Ooh, oh yeah, I should have said here. One more to list up here. Odd roots, like y equal to the cube root of x, or f of x equal to the 7th root of x. Those are defined everywhere and are continuous everywhere. And finally, lastly, functions that are continuous on their domains, even roots, like y equal to the square root of x, or any even root of x. So this list is by no means exhaustive, but it's just meant to give you a quick kind of idea of what kinds of things are continuous. So when I'm looking back at this previous example, I was like, oh, I don't have to worry about any of these things where they're not changing from one to the other, because I know that this polynomial is continuous wherever it's defined, and this exponential is continuous wherever it's defined, and this polynomial is continuous wherever it's defined. So I'm not thinking about where they might also be discontinuous other than where we're having groups. We have a few minutes left, so yeah, let me actually quick gander here. Sure, that's not a bad question. Let's look at, yeah, let's do this. Let's say my function was f of x equal to, sure, fine, x squared minus 36 over x minus 6 when x is not equal to 6, and 7 when x is equal to 6. So I'll point out, we already know that this function is continuous for sure everywhere except for maybe where. Or is it maybe not continuous? Yeah, because the other piece, whenever x is not 6, that function is a rational function. Rational functions are continuous wherever they are defined. But it's not defined to be at 6, so right, that's where we might have a problem. So we're going to do the same sort of thing. We're gonna look at the 3 things for continuity. So continuity. So 1, is it defined? Is it defined? What's f of 6? Right. I know it feels kind of silly with them, like they told us what it was. They said if x is 6, then your function is 7. F of 6 is exactly 7. That's it. All right, how about the limit? So we could do a left and right hand limit, but the thing is, this function is the same on the right and left of 6. When x is not 6, that means when x is bigger than 6, or when x is less than 6, this function is x squared minus 36 over x minus 6. So we don't really have to do a left and a right. We can just say, I'm going to do the limit as x approaches 6 of f of x. And when x is approaching but not equal to 6, our function is this piece up here. Okay. Now, interestingly, this factors. And you get x minus 6 times x plus 6 over x minus 6. The x minus 6's get to cancel. And then you have the limit as x approaches 6 of x plus 6, which is 6 plus 6. So the limit exists, but it's not the same. So we can say that this function, f of x, is not continuous at x equal to 6 because the function value, which is 7, is not the same as the limit value, which is 12. If the function value at a point and the limit as x approaches that point are not the same, then the function is not continuous there. But to be more specific, I would say that f of x is continuous everywhere else. So it's continuous on the interval from negative infinity to 6, union 6 to infinity. Now, a question that people would like to ask here is, what can we change this number here to? So, like, for example, what does k need to be so that this very similar function, f of x equal to x squared minus 36 over x minus 6 when x is not equal to 6, and k when x is equal to 6. So that function is continuous. And everyone should be able to look over here and see that our limit was this. And so if I make that k value equal to 12, then that'll make this whole thing continuous, because then the function value will be 12 and the limit value will still be 12. So we need k equal to 12. This is an example of what's called a removable discontinuity or a point discontinuity. If we were to graph the original function, the original function looks really like the line just y equals x plus 6, except we have a hole at 6. So yeah, there's 6, there's 12, 6. I can probably graph this without too much. Yeah, sure. The original function looked like this, with a hole at the point 6, 12 and a point at 6, 7. Clearly discontinuous. But then if you move that point up to 6, 12, then you fill it in the hole and you made it. So that's why it's called a removable discontinuity, because you can move that point back. All right, I should probably stop talking.